actual lecture. But sliding in the protocol, as I said today. I've asked my team to deliver it. Hopefully they will deliver it in the next 10, 15 hour, depending. Without it, it will depend on the actual slides, and will depend heavily on the actual tutorials to explain things properly. Starting today with the first half of the actual data link protocols, we are looking at the point-to-point protocol that we did not describe last week. We're going to describe the structure of it, the services that are being used by this point-to-point protocol, and some of the actual parts where something called byte stuffing as well. So, first of all, what's point-to-point protocol? What's that? Yeah?
Communication between two devices?
It's a protocol within the data link layer. Communicate between two end devices within the data link layer. Simple as that. So for you to actually enable the services within the data link layer, we said we need some sort of protocols. We said we have so many different protocols within the data link layer. For example, Ethernet, Wi-Fi, point-to-point protocol. We are going to discuss in details now. These are type of protocols within the data link layers. What are services we explained in the last lecture and tutorial? Some of the services that can be available within those protocols. Flow control, error detection, reliable service. These are some of the services that we explained in general. We haven't explained all the services. We have explained like a set of 5 or 6 of them. Okay? We're now looking at point-to-point protocol in details and what kind of services that point-to-point protocol provides. So first of all, you need to know that point-to-point protocol deals with one sender and one receiver within one link. That's it. That's the word point-to-point. You only have 2 parts you can send on. Sender, receiver. So the data is going between the sender and receiver on one link only. Okay? You don't need media access control. And why is that? What's the media access control first? So imagine you have 4 users trying to use the actual medium, the shared medium bandwidth. What do you need?
Communication bandwidth.
What do you need? Okay, well, what do you need if you need to enable the 4 users to use them simultaneously, on an order priority? What do you need? What? What's that? You need some sort of control. So you need some sort of medium control. You're allowing users to use them on a regular basis, on a simultaneous basis, on a priority basis. You need some sort of a control. That's your medium access control. We had a shared medium. We said we have, as an example, we gave classroom that any of you guys saw speaking all together, no one can understand anything, but you need some sort of control. And my role here is to ask anyone who wants to speak to raise his hand and to tell me what he wants to do, what he wants to speak, so everyone can understand. Similar to networking. You need to have some sort of a medium control you share to allow users to use the medium simultaneously on a priority basis regardless. So that's the medium access control. Why is it not valuable here? Why is this redundant here? Why do I don't need it?
Because it's only one sender, one receiver.
One sender, one receiver, exactly, just that one link. So in other words, putting it there will just add overhead, will just add delay to the actual service. I don't need to enable 2 speakers to speak on some sort of control medium. They can't speak regardless. When we are 2 users, one is sending, the other one will wait. The one finished, the other one starts sending again. This is very basic. Putting it there will just delay the service, will just add more overhead. That's why medium access control is not required within the point-to-point protocol. No need for explicit MAC addressing. Same principle. One sender, one receiver. MAC addresses are physical addresses between users. You will, at one stage, I'll explain full details of MAC addressing. At the 3rd layer, I'll explain in full details your IP addressing. There are 2 different things. MAC addressing is the one which is stored on your physical device. Your MAC, so for example, you have a PC. If you go to settings, any mobile device now, if you go to your settings, you'll find within your settings your hardware actual MAC address. And that's being stored, will not be changed, although there is some new techniques that can play with the physical address. But let's assume, for the sake of the lecture, when the time that we created, physical addresses cannot be changed. that's a sort of physical address that's called a MAC address. Again, why it's not really needed within point-to-point? The same principle. Two devices communicating only with each other. MAC addresses are not needed. So once in transmission, the queue only one place frame can go. First. Popular point-to-point DLC protocols. We have, again, when I say point-to-point protocol, this is what's being used at the moment within the internet. Within the data link layer, they are using point-to-point protocol at the moment. There are other protocols, as I mentioned, and other ones have been used similar to point-to-point protocol. It's called high-level data link control. But we are considering today only point-to-point protocol in details. There are different data link protocols, like the link access protocols. They come in different variations. They come with a B, a balance mode, a data transfer mode, or a frequency mode. There are 3 different modes of them. We'll discuss the lab B in full details after I explain sliding window protocol. So point-to-point design requirements. Again, they are very similar to the services we explained, but there are some services or requirements that are not available within point-to-point. We explain the general ones, or vice versa. We've not explained the full, for example, transparency of bits. Within the general ones, we are going to explain it in point-to-point protocol. Let's look at the framing. Packet framing, what's that? Very easy, explained so many times.
I think we had a
To payload.
the segment.
The payload, what does that have inside the payload? Not the segment, no. Yeah? What's called from the link layer 3? What do you call the message in the link layer 3? Datagram, exactly, thank you. So, what's happening? You are encapsulating the datagram within the 3rd layer towards the 2nd layer, creating what you call a frame. So, encapsulation is you're actually taking the actual message, adding a header file to it, creating a new type of packet. In this case, called frame. So framing is encapsulation of a network layer datagram in a data link frame. Carry network layer data of any network layer protocol. Again, I'm dealing with the actual datagram. This datagram must be coming from an actual protocol. So it might be either an IP protocol or different protocols available. So let's say it's available from within the IP protocols, the internet protocol. Ability to demultiplex upwards. You remember when we said that we are dealing, when I gave an example with the encapsulation, we had only one message and only one header. What if I have more than one datagram belongs to the same part? That means you have more than one headers, again, to that exact datagram coming from the link layer 3. So they all may belong to the same message, but they are divided into many datagrams with many header files, i.e., you have many frames within that message. So I'm sending the information from A to B. That message is, rather than one message, it's like 10 messages. When you're actually doing the framing to those 10, what do? Each part of it, you encapsulate it by adding a header file to it. So you end up with 10 frames, rather than one datagram. The same thing will happen when you send it to the actual receiver part. This will go back to the same shape where they had 10 places, rather than one. So they come in 10, put them together as a datagram towards the higher layer. Another requirement, bit transparency. What's that? What do you think from the name? What's enabling it to do? Anyone? It says here that you must carry any bit parts in the data field. Let's make that clear. In some cases, point-to-point protocol enables only some sort of data to be passed through the point-to-point protocol, i.e. putting some constraints from the layer 3. We need that to be removed. So if I'm using a different protocol, sometimes you have that issue. You put constraints on the data link layer to give you some, remember the pacing, the flow control? Similar to that, not exactly the same, similar to it, where you put constraints on the actual data. You're not allowed to go through unless it follows your own requirements. The point-to-point protocol will not do that. It will enable every part of the data to pass on from the higher layer, i.e. layer 3, towards the layer 2. That clear? Error detection. By now we know what's error detection. Detecting a flip of an actual bit, passing along from the source towards the destination. There is no error correction within your point-to-point protocol. Okay? Connection liveness. In some cases, there are errors happening within higher layers, nothing to do with layer 2. But with layer 2 issues, point-to-point protocol must flag there is an issue between the sender and the receiver, whether that's a physical part or a software part within the higher layers. The layer 2 must flag that. So, for example, if the actual signal between the sender and the receiver has been damaged for any reason, point-to-point protocol must flag that as an issue within the data link layer, not within other layers. So, in other words, point-to-point protocol can distinguish errors within the own service, i.e. within the whole layer. Is that clear? Again, these are requirements. Just straight requirements that point-to-point protocol must have. Okay? Network layer address negotiation. Endpoints can learn to configure each other network addresses. Again, the great part with the addressing of MAC layer, it's an auto configuration. What does auto configuration mean? If I would ask you now to create a network, what will the admin do?
Assign an address.
Assign addresses. What kind of addresses? That's the layer 2 addresses. That's your IP addresses. For example, if you go to your actual home environment, 2 machines. In some cases, you receive a message within your PC says conflict in IP address. Have anyone seen that problem with it? Where you have two machines having the same IP address, which one of them cannot work? That's an auto configuration, but it's having issues. Therefore, you need a manual configuration to change that autoness. In switch types, i.e. data link addressing, that will never happen. It will auto configure without having any issues. That's one of the requirements and one of the parts where data link layer comes to play. It's auto self-running configuration. Is that clear? We said point-to-point protocol detects but cannot correct errors. And we said point-to-point protocol is not a reliable service. So how can I provide reliability? Again, I'm heading here trying to show you exactly what will happen within sliding window protocol. Just keep in mind on this one. First of all, no error correction or recovery. No flow control within point-to-point protocols. These are non-requirements. Out of order delivery is okay. No need to support multi-point links and pooling. What does that mean? It's not a reliable service. Point-to-point protocol is not a reliable service because these are requirements that must be delivered within the reliable services. How can I deliver those? Can anyone remember? What's the essential information needed to deliver? Sequence number, thank you. That's the main thing, and that will be the main important role within the sliding window protocols is providing those sequence numbers. And how can you work on those sequence numbers? So error recovery, flow control, data reordering, all related or relegated to higher layers. So what does that mean? If in order for me to provide a reliable service, I'll depend on higher layers. Like for example, layer 4. Is that clear? Leaving reliable data transfer to transport layer is a philosophy of the internet. So why do you think they leave it to the higher layers? Why do I leave the lower layers without any reliable services? What do you think that? Anyway, we had 5 layers. We started with application, it was a physical. We said layer 2 is very similar to layer 4. But the main criteria that layer 4 had is that provide that reliable services. The example, why do I have a data link layer that without any reliable service? Why do you think that? Why do I leave it to the higher layers?
You might not need the reliable service.
Yeah, but why? You might need it, not need it, but why? Why do I leave it? If I need it, let's make it clear. I need reliable service, but I'm not considering it to layer 2. I'm considering it to layer 4.
Yeah.
Why is that? For example, why would I have both of them having reliable service? Why not just layer 2?
Because the service is actually quite reliable anyway, so it's not really.
When you say service, what do you mean?
Cable between, say, your computer and your router.
So they are less prone to errors in the cable level rather than higher layers. Is that right? What do you think so? Do you think that's right?
No idea.
Fair enough. to make it clear, we leave the reliable service to the higher layers, therefore you can deal with heavy load within the actual networking. Link layer does not provide heavy majority of errors within the actual data link layer. The heavy majority of errors happens with the higher layers. As you said, these other services can be provided within the higher layers, so therefore you need those actual reliability requirements. Data link layer do not need it because it will create more overhead, create more delay to the actual network. We leave it to the higher layers because it deals with more complicated, reliable requirements within those higher layers rather than the data link. My main thing I want to get out of the point-to-point protocol is it doesn't provide reliable services. In order to provide reliable services, we need to add another service over it. And that's where the signing the protocol came playing role. Let's look at data frame. How does it look like? If you look at the end, this is how an actual point-to-point protocol will look like. Exactly like that. You have a part where you have a flag, address, control, the type of protocols coming from the higher layers, the information where you have the data, i.e. payload, you just mentioned the payload, i.e. here is your datagram coming from, and then you have a check, and finally you have the flag. Let's move one by one. Flag. What's a flag? See the flag from the beginning and the end. What does that indicate here? Whenever the receiver see that sequence of bits, what does that indicate?
The head fire.
Sorry?
The head fire.
What's?
The head fire.
Nope.
No.
Is it error?
Nope.
The next acknowledgement?
Nope.
The next file is coming after the flash.
Okay, what does that next file coming? So when I have it at the beginning and the end, what does that indicate?
Next one.
So
Beginning and end.
just say beginning and the end, exactly. This flag indicates to the receiver. Just keep in mind, we are dealing with only bits. So if I have a sequence of bits, the actual receiver needs to understand what's happening from the other side. So if he sees that flag, 0 and 6 ones and another 0, i.e. 8 bits, if you see that combination of a pattern of actual bits, it's an indication that now I'm dealing with point-to-point protocol. That's it. This is how the receiver knows what kind of protocol I'm dealing with. For example, let's imagine this is a Wi-Fi. And instead of having this pattern of flag, you'll have a different one, indicating the Wi-Fi is starting. Okay? If it comes in the end, that means point-to-point protocol. Just end it. Yes?
Why do you leave it at the end as well? Because if the next one comes with the beginning one, when you just go okay.
When do you know you'll stop? That's not belonging to point-to-point protocol.
Are they both the same?
Well, let's answer that part. They are the same because they are indicating just an indicator. But returning to your question, if you just have a beginning, when will the system know it's ending?
Then you get the next one.
What does the next one mean? Maybe it's not the same protocol. So how can you stop? So let's imagine you have 4 point-to-point protocols. The same protocol is running within the system. Each one of them has data, error detection, and other requirements. So you say I'm starting with it and then continuing. The other one will never know that. I'll give you a good example. What happens if the data itself have the same pattern? What does that mean? Will it stop or will it consider it as a data?
Stop.
Well, it's a data. So I'm telling you that a flag has 0, 6 ones, and a 0. And then you had other details. Including those details, you had an identical flag but as a data. What will the system do? How will the system recognize this is a data or an actual ending of an actual flag of a point-to-point protocol? That's why we need the beginning and the end. And I'll explain to you how do we distinguish. I'll leave that just the slide afterwards. But that's why we need it. Because sometimes you have the same sequence of bits as a data. And the system will start saying that, is this the beginning? Is this the end? Is this a data? It needs to know. And I'll show you exactly how to distinguish the beginning and the end. But we need that to recognize. Okay. Is that clear at the moment? Flags. Why do I need flag? You hear the word flag a lot. That's the flag. Indicator. Enable the actual system, the receiver, to know you're dealing with a specific protocol. So if you have that pattern of the actual bits, that's the beginning. If it comes in the end, that's an end. How I distinguish it as a data, I'll explain that in the next slide. address does nothing, only one option. Okay, to make this easy. This is available to distinguish within exactly where is this being located within the destination. And it's always going to the same direction in the destination. And people might ask, why do I have it there then? Why do I leave it? Why do I just remove it if it's the same direction? Because the actual person who designed the standard of the point-to-point protocol left it in the future in order for it to add maybe more addresses. Until now, there's no new addresses. It's the same place it's going to. Just don't, this is not the address where it's going towards the direction. It's just an address within the actual layer in the destination. It's confusing, I know, but it's nothing to do with the actual addressing of the MAC address. This is just an addressing within the same structure of the point-to-point protocol. Control, again, does nothing. In the future, possible multiple control fields, the same as the address. This is a control part where you control the structure of the actual components within the data link layer, within the receiver. And until now, it's not been changed. It's the same. They leave it to the future, hopefully, to add other requirements to the actual structure of the point-to-point frame. What does protocol means? I'm dealing with what? I'm dealing with information coming from a higher layer. So when I say protocol, this means what type of protocol I'm dealing with within layer 3, and to which destination I'm sending it in layer 3 within the destination. That's your actual protocol. So for example, this might be IP address. So in here will be, this will be delivered towards an IP address in the destination, or this is coming from an IP address from the source. Information, what does that contain? What do you think? Data. So in here, what do you have from layer 3 again? Data graph. They come in different and variant sizes, but the main size within point-to-point protocol is 1,500 bytes of actual data. What's check? Error detection. Your actual error detection of cyclic redundancy check. That's your check. And finally, the flag. Fix. Great cycle. Hi. Yes, please. Great timing. The question is, what happens? We said that the main question is, if an actual data come similar to the actual flag, how can the system recognize this is a data, not a flag? We said the flag is 0, 1, 2, 3, 4, 5, 6, 0. And let's say this is passing on towards your destination. We had information before, information after. Any kind of information, don't worry. But this is data, not flag. We have something called byte stuffing. In other words, adding an extra byte to the actual combination to distinguish this is an actual data, not a flag. And this comes in this shape. So I'm sending this information. I'm trying to send 0, 1, 2, 3, 4, 5, 0 as data. I should provide before that an actual flag byte, a byte something called 0, 1, 2, 3, 4, 0, 0, 1. If I see that combination arriving towards the destination, arriving before the actual flag, so this is not a flag, this is an actual data. So the receiver will take that information, he'll read that part, and he'll understand this is what's coming is not flag. He'll discard that and take that as a data. That's it.
How can you tell the difference?
Because they are different. There's no should be one here. It's a different combination of bits. So it's stored that this bit means something is preceding me as a data, not a flag. Is that clear? The question is, what happens if this being sent as a data? As this ending. So imagine this is sent as a data. Not an indication there's a data coming, there's an actual data for this flag. What does that mean?
It's an odd another byte.
It adds another byte to it, creating a new combination, and so on. Is that clear?
So it keeps happening. So
Yeah, it never happens in that frequent. Well, if it happens, then it continues adding that bytes.
So why do you need the flags? I don't understand. Surely if the data's being sent, you can just understand that's data. Why does it need to know it's data?
Every data is being sent are bounded by a protocol. Is that right?
Yeah.
Each protocol has its own requirements and has its own services. If I leave the data open with an open protocol, the actual layers higher to the actual data link will not know what to do. So for example, you want to put reliable properties on that protocol and you're not indicating in any way. How would that know? There should be, so this is the structure. The data is actually a small part of the actual point-to-point protocol. That's why you need other parts. For example, within, for example, Wi-Fi, you'll have a bit here called the reliable RDT. Provided if it's 1, then it's a reliable service. This is 0, it's not reliable. That's with your higher layers. So again, you need those. So that's why you need a beginning and an end. So people, by people I mean, your end device will know what kind of protocol he's in. Returning to your point, is that clear now why I need the beginning and the end?
So with every byte of data, you say another byte to say it is data.
Yes.
Not a waste.
Sorry? Yes, it's a waste. But how many times that will occur in the reality? With that, only that pattern of bits, not every data, just that pattern of bits. So what I'm saying is, let's consider the data is 1101111. That's nothing to do with the actual flag. Is that right? Unless it comes in that shape, then you need to add that byte. Just to distinguish, that's not a flag, that's a data. Yes.
You keep saying n5, but on the example
Should be 8.
below,
If I'm not doing it, it should be 8. 8
it's-
bits. So maybe I've added the one extra, I'm not counting it. Does that make sense?
Is it adding a byte or a bit?
No, it's a byte. Changing it to the actual, when I say byte is 8 bits.
Okay. So maybe
That's what I need. Yeah.
I'm just getting confused here. The address that we're adding in here, is it the same address that
No.
we're adding on? No, I know not the direction for like 2 different devices. No, I know it's different. But on the head file, is it the same address? Because how many addresses we're dealing with for the
No, 5 or 6 addresses. They're called address.
But what's
But for example, I'll tell you, this should be clear within the next lectures. But if I send a packet, 3 main addresses I need to know. One is your MAC address.
okay.
That's addressing within your second layer.
Yeah.
If I'm sending that packet, I need to know your IP address. That belongs to your layer 3 address. I need to know something else. The port number. I think everyone knows the port number, i.e. 5 digits within your actual address. You need to know that as well. So these are the main addresses. Everything else deals with the small bits and structure of the actual bits of frame, of the actual framing, datagrams, segments, which you don't need to consider a reality. You don't need to understand that all, unless you go into full details of each one of those, why are they there, and what are they doing. What you need to be considering is those 3 other ones. That makes sense.
Okay, so which one we talking about?
No.
On them
You
3.
mean that address within the actual? Neither one of those.
Okay.
You
That's-
mean this one?
Yeah.
That address. That to do neither one of those. This is an actual structure within the point-to-point protocol to enable the sender to send it to the right place within the layer 2 in the destination, which is the same place. There's no other place. It's just that place. That's it. This is confusing, I understand. But what I need you to consider is what's MAC address? Well, when we come into details, how the switch, how the actual router define addresses to deliver to the right destination. These are nothing to do with the actual written on your envelope. So let's say you have an envelope with addresses. You have a street number, postcode, you have a house, apartment. Those 3 addresses nothing to do, that address in the structure got nothing to do with those 3 addresses. Those addresses are your MAC, your IP, and your port. Any questions? Okay. Let's go to the serious part. Reliable link transfer of data. I need your full attention, everyone. Those who are sleeping, those who are trying to sleep. Okay? I'm here starting with sliding window protocol. Okay? So let's see what does that mean. In packet switch networks, what is meant by reliable service? Come on, tell me. What's reliable service? Arriving it in sequence, arriving the packets in order, no duplicates, arriving with acknowledgement, no errors. We explained all of those. How is it implemented? I think we already explained that in full details, but we are going to consider those 4 parts in details. 1, a reliable transfer, the segments must arrive in order. 1, they must be in order. 2nd, there should be no duplicates. I.e., if I'm sending frame, let's call it 1, for any reason that should not arrive duplicates, i.e., 2 1s to the destination. That should be flagged, that should be recognized. 3rd part, no missing segments. If I'm sending 4 segments, 1, 2, 3, 1, 2, 3. If I send 1 and arrived, send 2 did not arrive, I send 3 and arrived. This should not be accepted, unless that 2 arrives as well, in that order as well. No transmission errors. Sometimes I send the packets from a source towards a destination but got lost in the middle. So no one knows where that packet went, i.e. a loss of packets. It's not being written towards the destination, it's not being arriving. That should not happen as well. The question is, how do I do that within an unreliable service with point-to-point protocol? Already said that we implement by adding a sliding window protocol on top of the basic service provided by point-to-point protocol. Okay? How can I achieve those? Already mentioned, we achieve this by providing a sequence number. That's the main part and the essential part of providing those 4 requirements. We have 2 types of error detection and correction. We have 2 types. 2 types. 1, something called go back N. Second one is selective repeat, or known as selective reject. I'll explain each one of them in details now. We are focusing on go back N, i.e. but I'll explain you both of them to understand the difference between the both. Let's assume you have 2 devices communicating with each other, A, B, and you send 3 segments, 1, 2, 3, arriving. Okay? Let's say I'm using go, back, and as my error recover strategy. Okay? Let's say first packet arrived successfully. Remember the 3 first requirements that we need. No errors, in order, no duplicates. Second one did not arrive. Third one arrived afterwards. What's not happening here? The order. So 2 did not arrive. I'm using go back N. What does that go back N means? How many packets, or let's call them segments, frames, arriving from source towards the destination, i.e. number 4, number 5, number 6, what happened to them? They will be dropped. So in other words, I received 100 and I did not receive 2. I drop everything until I receive number 2. Is that clear? What's happening? I'm ignoring all messages if 2 did not arrive in order. That's you go back in. So in other words, you go back to the one have not been delivered, wait for that to arrive, and then continue accepting everything else. That's the go back end. This one we're going to consider in sliding window protocol. There is another one called selective repeat or reject. That belongs to layer 4, and we'll leave it until we reach the transport layer. But let me explain it to you now. Same example, but I'm using, instead of using go back end, I'm using selective reject or repeat. Same thing. Use a different pen. Same example. A and B trying to communicate. First message, arriving. Second, not arrive. Third one, arriving. And let's say fourth and a fifth. In go back end, if I received 1 and did not receive 2, I'll start ignoring everything else until I receive 2 again, because I want them in order. In selective repeat or selective reject, what will the system do? Let's imagine there's a buffer. It stores number 1. Keep number 2 empty, do not arrive. Then number 3, it stored that. 4, 5. So it stores everything, doesn't drop any packets. And then wait for number 2 to arrive, store it back in its position. That's your selective repeat or selective reject. Is it clear what's the difference between those two?
Yeah.
We are going to use go back end rather than selective repeat or selective reject in our sliding window technique. Sliding window protocol can be considered a state machine, where you have variables changing from time to time between the sender and the receiver. And you need to track every change within those sender and the receiver. Events move the machine from one state to the other. There are variables which change when events take place. This will be clear in the next 2 slides. It's essential to be able to uniquely identify each segment to verify whether the first 3 requirements are satisfied. How can we do this? By using your sequence numbers. So how many sequence numbers do we need? How would you decide how many you actually use? What restricts the number? All of those will be defined in the next 2 slides. Let's go now to details of sliding window. Yeah, it looks pretty different. So, just look at it now. Just explain it in general and I'll explain it in details. This is the transition of information coming from your actual sender to the receiver. In this case, we have a sender A sending information to receiver B. First of all, is this a half duplex or a full duplex? Can anyone tell me?
Full duplex.
Oh.
Why? Why is it half? Why is it that's one? Half full. What's the difference? First of all, you remember I had a question in one of the tutorials. A student telling me that is a half duplex means if I'm sending any kind of information. Where's that? Is that you? Is it? You said he asked me that if I'm sending a data and message, and I received an acknowledgement, is that a full duplex or is that a half duplex?
That's
no,
half.
it's a half duplex. Because what's data is considered is actually only the message, the data, the information. The acknowledgement will not be considered as a data. This is what we call a supervisory frame. Meanwhile, the message is an I frame, a data frame, which I highlighted within the actual messages. It's called I to the sequence. So the I messages are the only information or the most important information you need to consider. When I say a full duplex, that means both sides send an I frame. In this situation, is there both sides sending? No, only one side is sending information. The other side is only acknowledging information. Okay? You need to keep that in mind. So the question says, how do I distinguish sequence numbers? I'll define how many sequence numbers you have. For example, I'll say your sequence number are 4. They range from 0, 1, 2, 3. And they even wrap around to 0 again. How do we know that? Usually I give you something called the n bits, and let's say that's a 2. There's an equation that says 2 to the power n minus 1 will give you the number of your sequence number. So that's 2 to the power of 2 minus 1, i.e. that's 4 minus 1 gives you 3. There's a 3 changeability of the 0, 0, 0, 1, 1, 0, 1, 1, i.e. the 3 numbers. But there are 4 numbers. Don't worry about the actual sequence. This is the bits you need to consider. So they are your sequence number. I always say in the exam or in the question, beginning, saying that you have 4 sequence numbers ranging from 0, 1, 2, and 3. If you go to 3, you need to go back to 0 if you want to continue sending information. They wrap around. Let's look at the variables that we have. Yes.
What do you mean it wraps around? Does it mean it can't be 3?
So if I say you have a sequence number, right, you are sending 5 messages. First message will be 0, second will be 1, third will be 2, fourth will be 3. What about the 5th one? Is it number 4? No, it goes back to 0.
Okay.
That one I mean. And that will be clear in a minute. You need to keep in mind, one side is sending information, the other side is only acknowledging. In this case, I have few variables. We said variables changes. If I return to the slide here, I'm saying that events move the machine from one state to another, where variables will change when events take place. We need to see how the variables is changing. It's already written, you have it in your slides, but let's do it again in front of you. I have the bus connection, where I have a terminal A in that side, and a terminal B in this side. Those are your end devices. Okay? What's your variables? You have, if I'm sending information, you need to have variable of sending. Can everyone see the whiteboard? Is it clear, everyone? Variable of sending, and I need a variable of acknowledging what I've sent. From the receiver side, you have one variable, and that's a variable of receiving. Okay? It all starts with 0. The actual machine between the sender and the receiver have a time scale. Everything is bounded by time. So we'll have a time. That will be in any way you want to do it. But usually we start with 0, going on towards 10, 20, depending on the question. So let's say we have 3, 4, 5, this means 1, 2, 3, 4, 5, 6. These are just seconds or milliseconds at the end of it. Okay? How information is passed from the source towards the destination. Let's say I send a message in the 0 millisecond. It takes 1 millisecond to arrive towards the destination. So I've sent it at 0, arrive and away at 1. So this is how it is. This is 0, 1, 2. So it's both sides. The time is followed with the both sides. Okay? I'm sending a message. That message, as I said, if it's a data message, has an iframe in it. So whenever you see an iframe, that's the data. We said we need to control those messages. What do we use? We use sequence numbers. Where do we start from?
0.
0. I have a rule says that variable changes whenever event occurs. So what do? Define that first rule. You have the variable of the receiver. If it's equal to the variable of the sender, then increment the variable of the receiver by 1. And increment the variable of the sender by 1 as well. What does that mean? I've sent a 0. We are starting with 0. Is 0 equal to 0? say we have another message going from 3rd millisecond, arriving at the 4th millisecond. What do you do? What's this? The iframe? What's the sequence number? It's 1. The question says, if variable of the sender equal the variable of the receiver. In this case, it's 1 now. What do? I increment this by 1. I increment my sender by 1. Look what I'm doing. I'm following the actual timing. When I'm sending, I increment it exactly in the sender. When I'm receiving, the 4th millisecond, I'm incrementing my receiver. So this changes with the sender and the receiver, not just one place. Let's continue. I've sent a message from 5 arriving at the 6th millisecond. What's that? Iframe S equals S2 equal to 2. Yes, you increment your receiver and you increment this sender. Yes.
Why do it was 2 sequence 3?
This is how it works. You start incrementing in that side, regardless of the sequence number. So if 0 equal to 0, you increment by 1. 1 equal to 1, you increment by 2. Those are the variables, those are your sequence numbers. They are 2 different things. Okay? Let's say now this side wanted to acknowledge receiving those messages. He sent something called, let's use a different pen, an RR frame or an acknowledgement frame. Let's say it's arriving from 3, arriving here, sending back in this place. This is an RR frame, or I call it an acknowledgement frame. When you acknowledge whatever you received. What did you receive until now? So you copy that 3 and you say I've received 3 and everything before 3. And in this side you'll acknowledge receiving 3 frames. Now tell me, is that clear or not? Okay, not bad, is it? Still simple. Nothing here. Okay, let's look back here, and I want your answers. First message is sent when from the sender. Where's the sender? That's your sender, and that's your receiver. First message is sent. When is that? 2 milliseconds. That's your timer. You can see the word time. That's your timer. Okay? It's sent at the 2nd millisecond, arriving at the 3rd millisecond. First of all, an iframe with a sequence number of 0. This is how you start. Is that right? You say, if 0 equal to 0, what I'm doing, I'm comparing the 0 with the actual variable. Are they equal? Yeah. I incremented it by 1. I incremented my sender by 1. Is that right? I've sent another message. You have them in your slides also. In the 5th millisecond, I send another iMessage, i.e. data message, with the sequence number 1. Is it equal to the variable of the receiver? 1. Is it equal to 1? I'm comparing this one to that. Yes, I incremented by 1, and increment my sender by 1 as well. Same thing at the 8th millisecond. Another message with the sequence number 2. Is the sequence message in the variable of the sender equal variable of the receiver? Yes, I incremented, and I increment my sender as well. Tell me what's that and what's that. One of you. What are those numbers?
0, 1.
So what's that first? 2. Why? How many sequence numbers do I have? Come on.
4.
4. Which are? 0, 1, 2, and 3. What comes after 2? So what should be that?
0.
3.
It should be 3. So you already have 1, 2, now you need to have 3. What's that?
0.
You cannot go to 4, you go back to 0. Is that right?
Yes.
Good.
1.
What would that acknowledge? So, first of all, if I hear 3, if 3 equal to 3, yes, I increment this to what?
4.
No, you cannot go to 4.
As 0.
You go back to 0. If 0 equal to 0, what do you put here? 1. So what you are acknowledging? 1.
1. What about if it's not equal? The variable is not equal.
If they equal, then they're out of order, and there's a mistake. They must be equal. If it's not equal, and I'll show you cases, a lot of cases where it's not equal. You want to break. Let's take a break and go back because I have like 8 slides defining this in details. Let's take 5 minutes.